Hello and welcome to this next lecture on fundamentals of acoustics. In the last class we looked at the physics of the piston or oscillating piston on a rigid sphere. And we described the physics using plots of this form, where there was a pressure in dB plotted here, okay, and one of the plots was the angular position from 0 to pi around a sphere. I said this region is the radiator part, theta equal to 0, theta equal to pi. At some distance, let us say r equal to 1, we are looking at the sound pressure in decibels and trying to figure out, okay, what is the behavior, why we have dips, why the amplitude goes up, etc. We did that last time. Now one thing I just want to emphasize is that the general pressure expression, okay, or even let us say phi, let me put a phi also, okay, it will have somewhat of the following form if it is driven by a velocity condition, like it is in this case and in a piston, in a baffle and the pulsating sphere. In all those cases it is driven by a velocity. So if the system is driven by a velocity, then the pressure typically has this j omega rho 0 in front, then the source strength will come somewhere, then a 4 pi 2 pi some dependence will come, and there will be a r dependence, radial dependence. This could be square root of r dependence also in cylindrical systems, but there is a decay with r as you move away from the source. Then you will have terms of the form which are functions of Ka, the Helmholtz number, okay. So you could specialize it to Ka very small, such as a monopole, or Ka much larger than 1, such as an efficient radiator. And finally there will be a term which depends on theta and phi, the angular dependence. So these are terms you can expect in a general expression for a pressure of a source, okay. I wanted to mention that. Now the third point I wanted to mention is that we spoke extensively about the pulsating sphere, okay. So now I want to make something clear here. If Ka is very small, okay, then of course either omega is small or the radius is small. If the radius is small, less volume velocity, it can push less air, okay, it is capable of pushing only less air, and therefore it is an inefficient source. So now if you look at the acoustical impedance on the surface, it is dominantly imaginary, not purely imaginary. We made some approximations. So there will be a j times some component which will dominate, but a small real component is there, okay, which accounts for the radiation, however inefficient it may be. Now if you want to measure this, however small it may be, power, if you want to measure it, if you remain close to the radiator in the near field, okay, then measurement will be erroneous. You can measure, but measurement will be erroneous, because there is a very large velocity component which is 90 degrees out of phase. With pressure. So, in measurements this velocity will bury, okay, overwhelm or bury the in phase velocity. Okay. Whereas we did a mathematical averaging, okay, 1/2 real part of P V conjugate we did, okay, but that is a ideal mathematical idealization where you get the answer you want by choosing the real or imaginary. In experiment you are going to measure an average. You will use microphones and all the setups and signal processing equipment, etc., and you are going to measure and you are going to average. Okay. So, there will be a lot of errors creeping in because the near field velocity overwhelms the far field velocity. The power is being radiated by a small real part, it is being radiated, there is no doubt. But we were talking of what is the dominant behavior. How does the radiator dominantly see the remaining space in that manner, okay, by ignoring or neglecting this, but it is there. So, now if you want to measure even the small component that is being radiated, you have to go to the far field of the small radiator. Okay. And then you will have plane wave behavior coming in. Okay. Then the particle velocity will be in phase with pressure, and you can measure and average and results will be accurate. Okay. Similarly, when Ka is large, how large we do not know, some value large. Okay. So, such that there is a real component of surface acoustical impedance and there is, let us say, an imaginary component also. Okay. Let us say the real part is dominant on the surface, that means it is kind of an efficient radiator. Okay. Even there you are advised to go to the far field, that means the genuine far field where you are satisfied that Ka is large, okay, Kr is definitely large, such that you are in the far field and the imaginary part is down. Okay. I wanted you to distinguish that part. Okay. We are trying to understand dominantly the behavior of a small radiator or dominantly the behavior of a large radiator. Okay. It does not mean it is not radiating at all, it is radiating inefficiently from its surface itself, but if you want to measure that small value, you are better off going to the far field. Okay. So, I wanted to mention this part. Okay. Just to nail the point, the power, time averaged power, okay, for this pulsating sphere is something like u0 square rho c by 2, k square is square by 1 plus k square square. Okay. This is measured on the surface. Again, mathematically you can do very nice things. So, it gives you. So, here you can see that if my Ka is much smaller than 1, okay, the power is proportional to Ka or k square s square, which is small. Okay. So, in measuring this small value, you will go to the far field and do it properly. Okay. Whereas, if Ka happens to be much bigger than 1, okay, then you will get u square. This is intensity, by the way, this is intensity, sorry, this is intensity. Yeah, is intensity. Okay, 1/2 the real part of PV conjugate into V conjugate, not power. Okay, you need to multiply by an area to get the value. Okay, so now this is going to be U0 square rho C byte. Okay, so it is independent of Ka. Okay, so now this is the dominant behavior of a radiator which has Ka large, and it could still have the real part and the imaginary part as surface impedance. So there could be a small component over here which could pollute your averaging when you measure. So here also you are advised to strictly go to the far field so that you get accurate measurements. Okay, so I hope this part is clear. Now we have been talking about Sommerfeld radiation condition, and we will look at it today. To just briefly talk about Sommerfeld, his full name is Arnold Sommerfeld. He was both a physicist and a mathematician. So he has written several books in mathematics. Okay, and his name is associated with this radiation condition. So many people, many scientists have some non-dimensional number named after them, Rayleigh number or Reynolds number and so forth. Okay, so I thought there is one condition that is named after a mathematician or a physicist, but then I looked up his biography. Amongst all his accomplishments, I found that 4 of his students were Nobel laureates. Okay. He did not get a Nobel Prize, but the other 4 students were Nobel laureates. Okay, I thought just mention it as a part of interest. Now, what is this Sommerfeld radiation condition? Okay, now our acoustic wave equation looks like this. And if we stick with the harmonic case, okay, that means e to the power j omega t. Okay, now one thing I thought I should mention, that when I write e to the power j omega t, in the same next line I do e to the power I omega t. Okay, so I and j I use interchangeably, so just please get used to that. Okay, both means square root of -1 to me. Okay, so when we do the harmonic case, this becomes the Helmholtz equation. Okay, so we write it as, let's say, p of x comma t is some function of space e to the power of j omega t. So that I get del square plus k square phi of x equal to 0. This is Helmholtz equation. Okay. Now if we think of this first of all as just del 2 del x square, then this gives a in x it gives a solution that is going out to the right and to the left. Okay, one right traveling solution, one left traveling solution it gives. Okay, but now suppose I have a system that is driven here and the system is infinite. It is driven over here, this is the x direction and the waves travel to toward the right. Okay, but the solution allows a left traveling wave. That is also a solution to this equation. Okay, so suppose hypothetically I use some basis functions to solve this problem numerically. Okay, and I solve it. It may happen that there will be a left traveling solution as part of the total solution, which is physically not possible because this is infinity. This wave that is resulted from this source will travel towards the right forever and never meet a boundary, never reach a boundary. And there is only this source, there is no other source towards the right, this is the only source. Without a source and without a boundary there will be no reflection, nothing can come back to the left. So left is not possible. So now along with this expansion or summation, I have to place a condition, I have to apply a condition, and that is should be mathematical now. Okay, such that the left traveling wave is cancelled. In our simple problems which were analytically done, we have an e to the power of minus jkx with an a in front which is a right traveling wave, and there is a b e to the power jkx which is a left traveling wave. Then we looked at the system, we said there is an infinite duct and therefore I do not expect a b to be there. So I set b to 0 by logical arguments. Okay. But when you are doing large scale problems with mathematics numerically, then you can't do this logical argument. Okay, you have to ensure that the left traveling wave, incoming wave is cancelled automatically through a mathematical condition. So that condition is called the Sommerfeld radiation condition. Okay. Now let us start simple. Okay, let us say I have a right traveling wave. I have a right traveling wave. Okay, and I am using the e to the power plus j omega t convention. So my right traveling wave is a e to the power of j omega t minus kx. Okay, so t and x are such that I am tracking this particular portion of the wave. I am tracking this portion of the wave. Okay, so omega and k are of course given and related. T and x are such that I am tracking this portion. Okay, so this part omega t minus kx is the phase. For a particular value, it gives me this peak location. Okay. Now at a later time, okay, at a later time what happens, which is, let us say, t plus delta t and x plus delta x, a later spatial location, at a later spatial location. So this thing will have moved, a little, okay, at a later time it has moved to a later space, okay, but then this value should remain the same so that I get the same peak. Okay. So what should I do? What I do is omega into t plus delta t minus k x plus delta x is equal to the same value psi. Okay. But if I open it out, what I have is omega t plus omega delta t minus k x minus k delta x is equal to psi, whereas this part is already equal to psi. Okay. So what I get is omega delta t minus k delta x is equal to 0. Okay. Or if I divide by omega, divide by k, c delta t minus delta x equal to 0. Okay. So c is a positive constant. So when delta t is positive, delta x has to be positive, so that this is 0. So this is a right travelling wave. And obeys causality. Okay. Based on simple calculations of phase, it obeys causality. Okay. Now we have to convert it to a mathematical condition. Okay. How do we do that? Okay. In contrast, if we look at a left travelling wave, e to the power of, let me call it b over here, we call it b over plus kx. Okay. In this case what we will get is that c delta t plus delta x will be 0, c being positive, delta t being a positive increment. I have to have a negative delta x for this to be 0. That means as time goes forward, the wave moves leftward, decreasing delta x. Okay. So this is not possible now. What we are saying, we have a situation where we have an infinite pipe as a source over here, and so a wave can only move rightward. A leftward moving wave is not possible. Okay. So now to bring out the mathematics, we will say that a pressure at x plus delta x comma t plus delta t is equal to the pressure x comma t plus del p by del x delta x plus del p by del t delta t. Okay. So now for a right travelling wave, what do we have? For a right travelling wave, this is equal to that. So we will set this to 0. Okay. Why this is equal to that? Because at a later location and a later time I get the same pressure. Okay. So I have del p by del x delta x plus del p by del t delta t equal to 0. Okay, this gives me the right travelling wave. Okay, or del p by del x plus 1 over c del p by del t is equal to 0. Okay, so if I say that my p of x comma t is some other p of x and e to the power j omega t, then this becomes dp by dx, okay, plus k times p. Okay, so what does this do here? What this does is I will get a minus. If you look at this expression, we look at this expression for a right travelling wave, I will get a minus j times k times p, okay, from the special derivative. Then I get a plus j times k times p, that is equal to 0. Okay, I don't need this part, I don't need this, I don't need this also. Okay, considering my p to be equal to a e to the power of j omega t minus kx. Now if we apply to p is equal to a e to the power of j omega t plus kx, okay, then I get jkp plus jkp, that is not equal to 0. Okay, so if I do del phi by del x plus I k phi of x equal to 0, if I create this condition, where phi of x is a solution to this phi of x, okay, because harmonic is anyway assumed. Okay, so then this condition, okay, d phi dx plus I k phi of x is equal to 0 will give me the right travelling wave. Okay, and it will cancel out the left travelling wave, because left travelling wave will not satisfy this. Okay, so let me just give an example here. Okay, so we have an infinite duct, with a piston at the left end, so I have a piston at this end and an infinite duct. Okay, and let us say I have now this del square plus k square satisfied by phi of x equal to 0. Okay, then the phi of x, this is like the simple harmonic oscillator, so this is equal to a cos kx plus b sin kx. Okay, and now suppose we are doing an FEM problem, we cannot go to infinity, we have to truncate the domain at some point. Okay, and if you truncate the domain, you will get a reflection. So how to truncate and put a condition so that I don't get a reflection. Okay. Now at the left end, of course, I will put a source condition. At left end will be a source, there is a piston source. Okay. Now at a certain L, I will use this condition, or I will apply this condition, which is d phi by dx plus ik phi of x equal to 0. I will apply it at a certain length, distance. Okay. So let us see, phi dash is minus ka cos kx plus bk sin kx, minus ak sin kx plus bk cos kx. Then I have plus ik phi, which is a cos kx plus b sin kx. All this applied at x equal to L, that must be 0. Okay. So let us see, if we do that, I have minus ak sin kl plus bk cos kl plus ik a cos kl plus b sin kl equal to 0. Okay. Now this will be satisfied if b is equal to minus ia. Okay. If b is equal to minus ia, what happens? Minus ak sin kl minus I a k cos kl plus I a k cos kl minus plus a k sin kl, that is equal to 0. Okay. So this relationship between the two constants enforces this Sommerfeld radiation condition in the 1D case. So let us see, let me put b equal to minus ia here. So my phi of x is a cos kx, b is minus ia sin kx is equal to a cos kx minus I sin kx is equal to a e to the power of minus I kx combined with e to the power I omega t. This is a right travelling wave. Okay. We imposed this condition on the assumed solution, and what that did was it chose constants a and b such that we have only a right travelling wave. Okay. So now if we do this for a 3D symmetric situation, okay, in a 3D symmetric situation, that means theta phi symmetry. Okay. Let us say if I have my solution, let us say phi r comma t given by a by r e to the power of j omega t minus k r, Now this is again 1D, so we will apply the same condition as this over here. Okay. So we will do del phi del r. If I do del phi del r, I get minus I k minus 1 over r a over r e to the power of j omega t minus j k r plus I k a over r e to the power j omega t minus j k r minus k r. Minus kr. Okay. So now what happens? You can see that this term cancels, okay, this term, but we have one extra term left over here. This comes due to spherical spreading. And it decays away as 1 over r square. So not a problem. We can put a limit r tending to infinity and it will be taken out. Okay. But now watch this. So this has been actually done for an outgoing wave. Outgoing wave. And this is the choice we want. These are plane wave propagating components. Okay. So it has cancelled that plane wave type propagating component. It has just left out the spherical spreading decaying component, which can be taken out with an r tending to infinity statement. But watch this. So r tending to infinity must be there. Okay. But now if we have the incoming component which we want to reject, okay, and what is that incoming component? Phi of r comma t is equal to a over r e to the power of j omega t plus okay, plus jkr. That is the incoming component. If we apply the same equation, okay, del phi by del r plus I k phi, if we apply, let us see what happens with limit r tending to infinity. What do I get? I get I k minus 1 over r a over r e to the power of j omega t minus j k r plus I k a over r e to the power of j omega t minus j k r with the limit r tending to infinity. Okay. Now with r tending to infinity, we have r in the denominator here, r in the denominator here. Okay. Now this has a plus sign, whereas this, the same term, also has a plus sign. Okay. So now, so what do I have? I have I k a over r e to the power of j omega t minus j k r minus a over r square e to the power of j omega t plus j k r plus I k, let us see, plus I k a over r e to the power of j omega t plus j k r. Okay. So now with r tending to infinity, all these terms here also go to 0. Okay. So, the left travelling and right travelling are not distinguished, because the r tending to infinity is taking them out one way or the other. Okay. In the other case, the plane wave components are opposed in sign, which is what we want. Okay. They are oppositely phased, that means this is going rightward, this is going leftward. But if the r tending to infinity is there, it is not choosing, okay, it is not distinguishing between the left and right travelling waves. So, now in 3D symmetric coordinates, what we need is limit r tends to infinity, of course, okay, to take out this component, and r del phi by del r plus I k phi of r. I am sorry, I k phi, that does not matter, equal to 0. As a result, what will happen is that this r will eliminate this r, no more r in the denominator, it will eliminate this r, okay, no more r in the denominator. Limit r tending to infinity, this 1 r remains, this will go to 0, that is okay, but this sum will double, it will not go to 0. So, it will not be satisfied with the left travelling way, will not be satisfied. So, this part will add and remain. So, this is the Sommerfeld radiation condition. Okay. So, now in applying this to the KH integral equation for exterior domain, we had come up with this equation, phi at a certain r dash is equal to integral on a surface g r r dash del phi by del n minus phi of r del by del n of g, and the surface ds 0 of r, plus we ended up with an integral at infinity, r tending to infinity, okay, and we had the same thing g r r dash del phi by del n of r minus phi del g by del n of r ds at infinity. Okay. Earlier we said none of these things, none of these expressions can survive infinity. So, just by that argument we set each of these terms to 0, we set this integral to 0 straight away. Okay. Now, what we say, okay, we are going to center it, let r dash be 0. Okay. So, if we do that, I have limit r tending to infinity, okay, and I am going to use e to the power of I omega t minus I k r over r, okay, as my green function. So, what happens now? I have e to the power of minus I k r over r, okay, then del p by del r minus p of r, okay, del by del r of e to the power of minus I k r over r square d omega, okay, that is what we have. This has to be 0. Okay. So now what happens? My del by del r of e to the power of minus I k r over r is given by minus I k e to the power of minus I k r by r minus 1 over r square e to the power of minus I k r, and we have a limit r tending to infinity. So we will drop this in comparison. Okay, so this is, we will keep it as minus I k e to the power of minus I k r over r. Okay, so then what happens? Then what happens is I have limit r tending to infinity e to the power of minus I k r over r del p by del r minus p of r minus I k e to the power of minus I k r by r square d omega, that should be 0. Okay, then what happens? Limit r tending to infinity r e to the power of minus I k r del p by del r plus I k p. Okay, the integrand must be equal to 0. Okay, we impose this at a certain radius. Okay, so that there is no incoming wave. So this is the Sommerfeld radiation condition in 3D symmetric spherical coordinates. Okay, it is also saying that by the time you approach infinity, okay, it's becoming a plane wave. Okay, the solution is becoming a plane wave. So this is the, so this is not 0 anyway. Okay, so we'll, this becomes limit r tending to infinity r del p by del r plus I k p is equal to 0. That's the condition. Okay, so with this I'll stop the lecture here today, and we'll continue in the next class. Thank you.